switch to issues of cartography. Last week when we met, basically we're looking at the subject of surveying, and I asked you to check on the definition of surveying. How many of us have done it? Hello? How many of us have asked you to go and look for the definition of surveying? Okay. So we know that the discipline surveying, and then we look at the definition, then we're looking at some basic concepts that are required when it comes to surveying. So I share with you the slide. After today's lecture, we'll have something on the slides from last week to what we will be engaged in, probably beyond. So that is it. We need to think of repackaging our lecture for next week because I'll not be available on Sunday. But any time from Tuesday up to Thursday, yeah, up to Thursday should be possible to arrange. Maybe because we can't get all the 4 hours in the evening, we'll break it into 2 hours of 2 sessions across those days. So the class reps, let's think of that and let's know what to do. That should be fine for us. So you have Tuesday, Wednesday, Thursday. To choose any 2 days that we can have an evening engagement. The time we can finalize it, I don't know if it will be 5 to 7 or 6 to 8 or 7 to 9. When you let me know, then we can inform our coordinator on our switch so that we can also keep in touch with us and ensure that we get our recorded session. So the reps, note that next week, Sunday, the online will be moved to the weekday after the Sunday, between Monday and Thursday. Once we get 2 slots of 2 hours each, that should help us. Do I have my reps on the page?
Yes, sir. I'm here.
Okay. I hope the others are I've also heard what I said. Good. So we want to continue the story that we had from last week and push it further to see what we got advanced towards. So last week we began and we were looking at what surveying is, which included a definition for which I asked you to go and look for it. Then we came to the history of surveying, and then we went to the principles of surveying. Importance of surveying, I didn't really touch on because I know you can get the notes and read it. That should be okay. Types of surveying. Yes, the major types of survey I mentioned is we have the geodetic surveying and then we have the plane surveying. Did I discuss that last week?
Yes, sir.
Good. And I went on to also look at the basic geodesy, where the science is about measuring and trying to determine the actual shape and nature of the earth. So we have some calculations, some radial distances, the likes. We saw that the figure of what we call the earth wasn't so nice at all. I promise getting you a video to share today. I hope I can trace my file. Not done that yet, but I hope I can trace it. Then I will share how our earth looks like and our attempts to model it. So mathematically, we model it with an ellipse, but the ellipse is not a perfect fit to the shape of the earth because the earth itself is really bad in shape. That's quite an irregular model. So it is always not easy when you want to find it, but somehow we have to make progress. So we've adapted models that are close, fitting certain areas well, but not fitting other areas well. But in a global sense, that is what has become to be accepted, giving all the distortions and difficulty as the more representative nature of the earth. So we have the topography, which is the surface of the earth. We have the ellipse, which when you rotate in 3D gives you the ellipsoid. And I also said that we start by thinking that our earth is spherical from the model of a sphere, football, a basketball. But as you grow and mature in the subject discipline, it is far from that. And I'm sure when I get the video and I'm sharing with you, I appreciate that. So we shifted our discussion from spherical to a spheroid. And a spheroid is anything that's not really a sphere, but has the nature and form of a ball-like issue, and you are rotating it or you are turning it around. You generate a spheroid, not a sphere. So that is the difference between the spherical, which is curved surface, general orientation, to a spheroid, which is more of a distorted ball-like object in rotation. So today we are going to advance that discussion further when I'm explaining the difference between the geodetic surveying and then the plane surveying and other types of survey. Then we'll touch a bit on the history of map making. This is an aspect because we are going to talk about maps. We are going to talk about survey methods that we use, but we will also, in the end, represent our information on maps. In fact, there's one area that cuts across about two disciplines generally. History of maps is found under map reading and interpretation. History of maps is also found under cartography, because when you talk of cartography, we are talking about the skills and practice of making maps. So then when did map making begin and what maps have we had in the past are all important issues. Nevertheless, it has found its way into my discussion in surveying, because when you talk about the types of survey and all of that, you end up now talking about how you represent your measurement. You do that graphically on paper, and that is what we call a map. So we'll be tempted to still talk about the history of maps a bit in trying to, as it were, cement our understanding on that. So let's advance the case that we were having when it comes to the types of survey. In the basic types of survey, I said, usually when you talk of types of survey, people's mind or the reference point is talking about the shape and nature of the earth with respect to surveying. So when you talk about types of survey, we are looking at geodetic survey versus plane. There are other forms of categorization or classification of survey. Some we use the instrument at the center of the activity to do that. For instance, that's what we call the chain survey or chain surveying. The chain is the instrument that is dominantly applied or used for recording. You can have GPS survey. You can have total station survey. So I have a few here and we'll discuss generally what those issues are. And then we'll advance it. So last week, we didn't have on the slide as I'm showing to you now, because this one is talking about the classification. But we can bring that discussion under the classification of surveying when we are interested in the size and shape of the earth. Then we'll talk about geodetic versus plane. Nevertheless, I did talk about the types of survey last week, and I mentioned the two. We will still advance the discussion with that a bit and then connect it with this classification of survey. So what are the issues when it comes to the issue of the types of survey? There are two main forms of it. By looking at the basic geodesy that we did, which is looking at the nature and the shape of the earth. So generally, you can see that the surface of the earth is generally curved. But this curvedness is more pronounced when you are talking about large areas, far distances. When you compare the globe nature of the earth, then the curved nature of the earth will come into effect. However, when we are dealing with local environment, small areas, engineering works, community engagement, town planning issues, even regional planning issues. Within those domains, you are taking CCMA, for instance, as a metropolis. When you are in that, even the central region, if you take that as a block, when you are doing discussions around that area, we assume the earth curved surface is not so pronounced and apparent because of the small or short distances. So in the presence of small area or short distances concept, the curved nature of the earth can be assumed to be flat and there wouldn't be much difference in issues that we have. So when we are looking at geodetic surveying versus plane surveying, one aspect is looking at accurate survey where the curvedness or the curved nature of the surface of the earth will impact on your measurement. So if it's about distance, you will measure between two distances. It's going over a long stretch. The curved nature of the earth, which you call curvature, will impact the measurement. So how do you accurately determine distance between 2 points when it involves a very large distance and the curved surface is impacting? So all types of survey you do with high accuracy, where characteristics of the surface of the earth, curvature, is not ignored, but incorporated in calculation and computation to get things still right, we call it geodetic surveying. The other counterpart, known as the plane surveying, assumes that you are working in a small area. So if I'm working in a small area, then relatively, I'll be dealing with, although it's an arc or it's a curve, because of the short distance, it looks like a straight. Let me try and do a demonstration here for us to see. Let me see if I can get my geodesy diagram back. Yes. So let me use this one for the purposes of the discussion. I'll come back to the other issues. Like I said, you'll get a slide much organized, sent to your reps. We'll send it to you. So let me, for the purpose of this discussion, blow this one up. And then let me still zoom in further. All right. And Let's look at this scenario. This is the actual Earth shape. This is the more of the mathematical model. Whichever way, the explanation will still come out. So let me pick 2 points. The first point, I'm using a black line for my discussion. I take a point here, then I take a point here. Now this is a global concept, so this is a very long distance out. Jacob, your hand is up. Okay, maybe it was a mistake. Good, so we have this long, and you can see the curved nature of the black line. But I'm looking at something around this pole and then something somewhere there, but that's quite a distance in terms of the globe. Now here you see clearly that the bending of the line gives you the curve, which is so pronounced. But if I am working within small areas, so that now the point I'm considering, this may be A and this may be B. Now I have this same A, but now I have a C, which is just here. So there is an A I had here. There is a B I talk about there. And there is a C I'm talking about now. Between A and C, the curve is showing. So you cannot assume and treat it as a straight. Because when you do that, it means you are connecting this straight to that. The two measurements will have differences. There will be large errors. But you say you want to do accurate measurement. So accurate measurement, large areas, large distances, you cannot assume that the surface of the earth is flat. The curvedness will be there, curvature will be there. You have to know how to handle that. It leads to complex mathematical expressions and scientific approaches. That's the difficulty with the geodetic surveying. So nothing comes simple and easy under geodetic surveying, but it's because you are seeking to get an accurate resource, irrespective, and still being mindful of the true nature of the surface of the earth. But when you look at between A and C, although the arc is still there, it's not so pronounced. It's as if a straight line can be generally okay to fit when you connect A to C. And that is what we call the plane surveying. So there are characteristics that are usually perceived of geodetic survey and then plane survey. One of them is the area. And the statement is that usually with geodetic surveying, you want accurate measurement. The area you are dealing with is more than 250 square kilometers. That's the area. It should be more than 250 square kilometers. So when you have such an area you are dealing with, then you cannot say that you are assuming the earth to be flat, the surface. So you have to take curvature into consideration. And the models you apply so that you still get accurate measurement makes your analysis and survey work geodetic. But if you are looking at plane surveying, then the converse is what you need. Your area should be less than 250 square kilometers. So that is one of the analysis and the considerations for geodetic application versus plane. Another thing is that when you are measuring distance between 2 points, as I'm showing with this arc, you are not dealing with a straight, you are dealing with an arc, ARC, or a distance measurement which is along a curve. A distance measurement which is along a curve. So you have an arc to deal with. But when you are in the plane surveying between A and C, small area, when you assume curveness or curvature is absent, when you are connecting A to C, it can be treated fairly as a straight line. And so therefore you deal with straight lines and planes, but that is not possible with geodetic surveying. So note that. So this is the second point. First point on area. Second point is saying that within the limits as defined. In the case of geodetic, distance between 2 points is modeled after an arc. But in plane surveying, distance between 2 points is modeled as a straight. And you can see clearly look at the arc nature between A and B, and then the same arc between A and C is almost like a straight line. So plane surveying will work between A and C nicely, but geodetic will have challenges. When you have A and B, plane cannot work because the curveness of the surface of the earth is showing. So when you still apply plane surveying rules and methods, you will end up having errors with accurate determination of distances and angles, for instance. So that is with the plane versus geodetic. Another property, and like I advised you last week, whatever I'm saying, have your jotter and take your notes. The slides will come, but they will not contain so much of what I said. So every lecture, even if you have a material of any, listen to the lecture and make your notes. Shilankra, you have your hand up.
Yes, sir. Sir, so please, under the plane survey between C and B, what
Yes, that
thing?
one too cannot be treated under plane
Okay.
because
Is there?
the condition definitely would be abused. That's 250 square kilometers between C and B. It will go beyond that area.
Okay, very well. Thank you.
All right, you're welcome. Good. So that is the issue. So number 3 on the plane versus geodetic. Another characteristic is that in the geodetic, you cannot ignore curvature of the earth. You consider it, you look at it, you use it, you factor in when you are doing analysis and computations. But in plane surveying, you can ignore the curvature of the earth and assume flatness. The difference is not much to affect the accuracy of your work. Then the last one is that within the plane surveying, the surface that we deal with, that is if you are treating the surface of the earth, the surface of an orange. The surface of an orange is curved. That's what geodetic handles. But under plane surveying, where the area is very small, the curveness will not show so much. So you deal with a plane surface, a flat surface, like a sheet, like an A4 sheet. That's how the surface of the earth may be assumed when you are dealing with the plane surveying. But when you are dealing with the geodetic, then the curveness will be apparent, and therefore it has to be considered. So whenever you do a work where you are not considering curvature, then the assumption is that you are using plane surveying approach. But then there should be that condition met that you are working in a small area that is less than 250 square kilometers. Other than that, there are still going to be errors with your work. So now we go to the classification, and I'll just mention them as we go along. But I'll ask you to do some reading around. It. So that is what I will suggest you keep in mind. So going back quickly, I come back to my classification of surveying. Like I said, in some literature, they will deal with general broad-based heading called classification. And then what we just did, geodetic versus plane, will be captured under the size and shape of the earth. So when you are looking at surveying based upon the size and shape of the earth, you consider it in two folds, geodetic surveying or plane surveying. Other literature don't bring it there, but they will treat it as types of surveying, the major types of surveying. Then you have geodetic versus plane. Then there are the kinds of survey or classes of survey where what I'm saying now comes in. So for me, how I package it, I am looking at cell classification, but I'm dealing with classification based on instruments. So the first one that I have there is the chain survey, an instrument that allows us to do measurement, but was typically metallic in nature. And below is the image of how the chain looks like. So they are metal links. The breakdown is what you are seeing now. There are metal links here. That is how it looks like. They are metal links. And these metal links are connected with rings, small rings. We call them connecting rings. So there's a link which looks like a bar, and the end has been coiled. So this is the coiled end. But between one link and the next link, there are three rings. One is from this end, the other is from this end. There's a middle one that joins the two. Then, after some number of counts, there are metallic tags. These are the metallic tags. This one, for instance, is found if it's the 100 meter or 100 feet concept. Most of it, this one is found at the 10th link. So you count from here, this one link, two link, three links, that way. By the time you get to 10, you see this metallic tag put in the middle, like you are seeing in the example here. So this one is for the 50th link. But this is for the 10th, 20th, 30th, 40th. And they have different designs. This one looks like a jar, a water jar. This one looks like an open or scissors, open scissors. But here, it's more like a fork with the zigzag, and then the pointings are three. Here, pointings are two, 1, 2. Here, pointing is 1. So this 10th lane, this 20th lane, this 30th, 40th. Then when it gets here, it looks like the earth pot, the earthware that we put water in and we drink. So that one is more bulge at the base for volume compared to a jar for drink. Okay, so these are called metallic tags. This side is called the handle, where you hold to measure. But the whole thing is metallic. As a result of that, it's very heavy to use. And usually when you are drawing or pulling it apart to measure distance, and the distance is quite extensive, you struggle to keep straightness because it's metallic and heavy. So that is with the chain survey. We are going to treat it in detail, where we look at that practice of the chain surveying using the chain for measurement. It's one of the traditional or classical methods. It's no more in use because we've improved upon instruments, distance measuring instruments. And even now we have the lasers that are doing very good and wonderful measurements. So we don't use the chain anymore. But as part of the lecture and knowledge gathering, we touch on it and mention it a bit. So that is it. So that is how it looks like here. It has been coiled and then tagged in the middle. The ends are what you are seeing at the top. This is how the ends looks like. The handles. This is how they look like. But then the whole thing has been coiled this way, zigzag, and then it has been brought together, and that's how you see it. And that is the chain. There are two forms of the chain. We have the engineer's chain, and then we have the Ganter's chain. What is the difference between them? Find out. One is longer than the other. Who is the longer one? Find out. The longer one, what is the length? Find out. So note all those points and then read around it. And I want to believe that you have started learning. Don't wait to the end. You'll be hot. You have pressure on your mind trying to learn and to remember. All right, so that is the chain. I go to another kind of survey that is looking at the instrument at the center of the work. We have the level survey. The level survey is an operation we conduct through a method we call leveling. And the idea is to determine height of points on the surface of the earth. But because the instrument at the center of the activity is the level instrument, we classify that type of survey as level survey. That level instrument, there are three types. The old model, we call one the dumpy level. D-U-M-P-Y, dumpy level. Then after the dumpy was developed the tilting level, T-I-L-T-I-N-G, T-I-L-T, tilt, tilting level. Then we came to the more modern one, which is the automatic level. So in surveying, when you are talking about the level instrument for leveling, the old generation, we have dumpy level, then to tilting level, and modern one, we have automatic and digital. Automatic and digital. So that is it. So level surface is there. You can imagine you using a compass, and that one too will come to it. So you can have what we call a compass survey. And the activity when you are conducting it, you will say you are undertaking compass surveying. So you can run a compass survey where the instrument is called a compass. With a compass, it's not in the slide here, but we'll talk about the issues of that in another domain. The compass measures directions. We call it bearings. But the bearings are magnetic bearings. The bearings are magnetic bearings. We'll talk about angles and bearings later, and the compass will show up again. So you can do compass survey, just like I'm showing you. So these are how the designs are. If it's the level instrument, you have a long pole. We call it the leveling staff, and it will be moved from point to point on the ground. Then the instrument is set up at a location, and an operator is behind it. The legs of the instrument is called a tripod. 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 3 legs. Pod is stand. So tripod means a 3-legged stand. 3-legged stand. So you fix the machine on that. The leveling staff does not have any tripod, but some for high accurate survey may have a bipod. It's a 2-pole. You fix it to the back and hold it there. Or it will be attached with a bubble. We call it the leveling bubble or a circular bubble to ensure verticality of the staff. Because this pole must be vertical from the ground for the one reading from it to have a good reading. So that is with the level survey. Then we can have photogrammetry survey. Photogrammetry is a method or approach where we are making use of photographs for measurement. Photographs for the measurement. But the science is that usually the photographs are taken by cameras that are put on an aircraft. That's why you are seeing that picture below. So as the aircraft flies in the air, you will see it as an aircraft just flying. But it may be conducting a photogrammetric survey. In that sense, it will capture the ground, the earth surface, in the form of pictures. So all that you are seeing below here are pictures. Pictures. So this is one picture, this is a second picture, this is a third picture. And the pictures will be processed and then fused together in a scientific way. Then information will be gathered from these pictures or measurements will be made from these pictures. So photogrammetry, the photo there is for photograph, but the grammetry is measurement. So measurement from photos, photogrammetry, or measurement from pictures, photogrammetry. So here to the instrument is the photograph. The photograph. In fact, it's a product actually, but it is called instrument because you need a camera to do that work. So we call it the photograph, but the survey work is actually extracted from the photograph. The camera will contain the film to capture the ground, but the measurement is captured from the photograph. So that is why we call it the photogrammetry. Another one that we can have, which is not here, but I'm still discussing it, is the GPS survey. GPS. G as in girl, when you're spelling a girl. G, then P for position, and then S for school or system. But the meaning of GPS is global positioning system. A kind of instrument that helps you to tell your position on the ground, anywhere you are around the world. So that is a GPS. So when you run a GPS survey, the understanding is that you are using the GPS instrument dominantly for your work, for your measurement. That's why we call it GPS survey. Another one is total station. Total station. TOTAL. Station. All of these instruments will be describing generally them, and you have to take note. You need to know what the work they do, the functions of each of them. You have to know it. Good. So we can have total station survey. Total station survey. So I've mentioned GPS, I've mentioned total station, I've spoken of compass, I've spoken of the level, I've spoken of the chain. Photogrammetry has now transformed itself into drone measurements, the UAVs. It's the same principle, but they are using a smaller aircraft of a sort, and the scientific approach for determining our solutions and measurements has become more sophisticated than what we used to principally have as photogrammetry. So I've spoken of the types of survey based upon the instruments involved. But that is not all. We can also have classification based upon the purpose of the survey. So we've dealt with the first bullet, instrument involved. We are looking at the second, purpose of the survey. Suppose I'm interested in getting you information about water bodies only. Water bodies only. They can be pond, they can be drain, they can be river, they can be stream, they can be the ocean. We are talking about water bodies only. I can run what we call I have some hands raised here. Is it Nolly?
Yes, sir.
Yes.
Sir, when you were talking about the leveling survey, you mentioned the modern one as automatic and then digital, and then you
There is
also
there is
mentioned
there is there is automatic, and there's the digital. We still incorporate the automatic. So usually the digital one,
okay,
we don't add the automatic. We just tell you digital level, but it incorporates the principle of the automatic level.
and then you mentioned the previous one that was being used before the
We have
automatic came.
the dampy level, and the tilting.
Please, can you spell it for me?
The dampy is
The
DUM. D,
DUM
not BO, D, dog.
D
D
Dumpy.
U
Okay,
DUMPY.
okay,
And the other one is tilting. TILTING.
tilting. Okay,
To tilt, turn it
okay,
up
all
or
right.
down.
Yes, sir. Yes, sir.
Okay.
Dumpy and tilting. Okay. Thank you very much, sir.
You're welcome. So remember to remove the hand then. Okay, you have Isaac Amwakon also having the hand up. Okay. So we come to the purpose. And I was saying that you are interested in mapping water bodies. It could be pond, it could be um, a pool, it could be a swimming pool, anything that is water that you are interested in mapping. But the main ones are the natural forms, like ponds, rivers, streams, whatever. So when we come and you are engaged in that type of survey, we can describe your surveying as hydrographic surveying. Hydrographic surveying. So why hydrographic? I am interested in mapping water bodies. Just like another one can be topographic surveying. Topographic survey is a survey of an area to measure all things natural and man-made. And in addition, you pick what we call spot height so that you can process and get contours to give us the nature of the ground. So whoever does that type of work, you can look at the nature of the work they did, the purpose of the work. And topographic maps are done or conducted to record all things natural and man-made around environment. All things, if it is possible under the scale of the map, all things natural and man-made. So it is usually a first point of call. If somebody wants information about a place, you want a topographic map of the place. You want a topographic map because the purpose is to give you everything, both natural and man-made. Jacob, you have your hand up.
Yes, sir. Sir, I was going through a particular document and I saw something like hydrological surveying, but it's also talking about water bodies and what you are discussing here. So I don't know whether it's different from the hydrographic survey that you are talking about. Yes.
Hydrological survey is water bodies generally plus some geological effects, including at times soil. Did you hear my explanation?
Okay, sir. Yes, sir.
Yes. But when you talk of hydrographic surveying, then it's purely water.
Okay.
Okay. So at times you can use the hydrological to substitute that, but the hydrological goes beyond just the water body.
Okay, sir. Thank you very much.
You're welcome. So I've mentioned hydrographic or hydrological, as our brother have said. I've mentioned topographic survey. You can also have cadastral survey. When you are interested in mapping people's plots, we call it parcels. So when I give you a cadastral map, it will be purely parcels. It will show the drawing of the length and breadth or whatever, the shape of the land. But there will be points to define the boundary. So that's cadastral survey. So when you're talking about parcels, ownership rights and issues, you need to build or you need to do a cadastral survey. And the cadastre is CADASTRAL, cadastral, if you want to use adjective. But the noun is cadastre. Cadastre, that one it is CADASTRE. But it just means people's plots and who owns what, which belongs to who. That is the nature of that. So when you want to pick people's plot, like in a residential area, and show it on a map, you are not interested in the road network there. You are not interested in the vegetation there. You are only interested in the plot and probably access points. So the road can be a minor addition or it can be exempted. The position of the plot itself will give exposure to the road network. So you will see the road system automatically. So that is that. You can do what we call mining survey. Mining surveys are usually typical of the mining areas, and it's done especially by mining firms to have an idea about their environment and space, and as they mine, to be able to come up with maps that show pits and where the mineral has been exploited already, areas that are still potential for exploration and the like. So everything's about the mine environment. So you cannot do mining survey in an urban space. Not possible. Mining survey is only fine around the mines where the mineral is. where the mineral is. So that is that. You can also do astronomical survey, where you are interested in measurement to celestial bodies like the moon, stars, and the like. And survey does that, but it's not a common thing when it comes to social science and social studies, because it's more of geodesy. People who are interested in knowing the size and shape of the earth accurately, then they want to also determine position accurately. They go into that. So if you are being trained as a surveyor, it's one of the environments you will be learning your survey methods in. But from the social sciences, it may not even be heard. So that one too is a possibility. So the purpose is to map celestial objects and use them to determine measurement of others, like location on the earth. So that are a number of them that I've spelled out. I may not have done an exhaustive work, but generally I've given you about 5 or 6 of those.
Please, so you said the purpose. Please come again.
In the
The purpose.
astronomical, the purpose is to make measurement to celestial objects. And the celestial objects, the measurement to them will help you to indirectly determine position on the surface of the earth. So at times you want to know your location on the earth, but you rather read to the stars, you read to the moon, you read to the sun. So the idea is you are reading to celestial objects. That's why it's called the astronomical. But the essence really is to determine position and measurement on the earth. So when we come to look at your data of the survey work, of the field work, we will see you to be recording to moon, stars, all your recordings about those things. But the processing will help you to determine your location on the ground, on the earth. All right. So we proceed from there to the next, which is looking at classification based upon the nature of the survey. Where are you conducting the work? The nature of the survey. Like I said, for the purpose, I've not exhausted them, so be open-minded when you are reading literature and other books. For instance, I can be doing what we call agricultural survey or agricultural surveying. Those are the surveys usually done or conducted over farmland, just to know the size of your farm, what is grown there. There's even now a current one we call it precision agriculture. How to accurately apply fertilizers and other things to farmlands to maximize yields. So everything that you'll be measuring and then recording, you see that you'll be talking about farm produce, farm the boundaries, So that one is there and a lot more. But the fundamental thing is that it's looking at that classification based upon the purpose of the survey. What do they need it for? Why are they doing that survey? The end use. All right. So now we come to the nature. Now, when we come to the nature, it's talking about spatial effects. So nature, you can have what we call ground survey. Ground survey, for instance, total station survey is part of ground survey. Why? The instrument and the things they are doing is over the ground. But I'll call it total station survey, and I'm right because I'm looking at it in terms of the instrument at the center. Somebody can also be watching me and say that you are undertaking a ground survey. That is also correct because his classification is based upon the nature of the survey. So you can have surveying activities over ground, over the ground. Then we can have surveying activities in the air. Photogrammetry is air. Drone is air. When you are doing such things, we say you are conducting area survey. And the area is spelled as AERIAL. AERIAL. So I've spoken of ground survey. I've spoken of area survey. And I've also spoken of the last one, which is in fact these are usually the two main ones. Uh, Space survey is not part. Space survey belongs to another discipline we call remote sensing. But for surveying from traditional to contemporary models, we took up nature of survey in two areas: ground survey and then area. In fact, there is even underground survey, but underground survey is typical of mining areas. Uh, Mining areas. But in advanced countries where, for instance, they can have train linking towns, but the trains are going underground, you can have underground survey as well. But the main one that we tend to talk about is ground survey and area survey. Ground survey and area survey. All right. So that is just a brief of the issues under the type of surveys and the likes. The last on that aspect has to do with the basic survey mathematics that we have to look at. Sorry. It's not in the slide here, but it's in my summary. Here. Basic survey maths. What are the issues? With basic survey maths, all that we are speaking of, maybe if your hand is up.
Yes, sir. The area and then the photogrammy. What is the difference?
Area survey is a general application looking at the environmental or the environment within which the surveying was being conducted. So when I use an aircraft with cameras on it, which will lead to photogrammetry, is under area as well. If I fix the same camera to, let's say, a balloon, a hot balloon, so that the hot balloon is flown in the air and takes the pictures, it's photogrammetry, but it is still area. Area is looking at the environment. Photogrammetry is looking at the product leading to the activity of measurement. So photogrammetry is looking at using photos. So the photos were gotten when the balloon or the aircraft went into the air. And right in the air, the surveying activity has started. Because it is from the air that they will take the shots. So if it is a survey activity and you began by being in the air, we can consider it as an area survey. But then you can look at it also from the perspective of product or instrument or the main issue at the center. So yes, you can have photogrammetry as a discipline. In fact, it used to be a popular discipline until remote sensing came up and now drones, and the name seems to be dying a natural death. But it is a big, broad issue which encompasses aircraft with cameras flying and taking shots of the ground and processing it. It can be done with balloons as well. It can be done with helicopters. Anything that will put us into the air so that we can get shots of the surface of the earth from the air is fitting into photogrammetry. But when I perceive how you did the work, you have to be in the air to take the basic and fundamental information. I can also say you are doing area survey.
Thank you, sir.
You're welcome. So when we talk of basic survey mathematics, what are the issues? All that this aspect is trying to draw our minds to is that we will do measurements as far as surveying is concerned. But these measurements don't end in themselves. They are processed further. Even the measurements that are done, at times they are based on certain science and computations. So we need to have some small fundamental understanding of some kind of computation. For instance, you should be able to add figures up and get totals. It's a fundamental mathematics in surveying. You should be able to understand that when I have a long distance to measure, but I have a tape which is not as long as the distance, how do I accomplish my work? I measure in pieces and I add them up. It is mass. I need to appreciate the use of, for instance, SOHCAHTOA. When I'm dealing with a simple right angle triangle, it's part of the survey mathematics. So what about Pythagoras theorem? When you have a when you have a right angle triangle and you have an angle there, a display there. Let me try to do a demonstration with that. So I have this right angle triangle. This is the right angle, it's somewhere here.
Sir, please, Mommy, how about
Hello? So you have a right angle triangle. I see my drawn triangle.
Yes, sir.
Okay. Now, if I deal with this angle, for instance, when I call this angle theta, in simple trigonometry, this is the object. It's a right angle triangle. Here it's 90. So when you add these two angles, it will be 90. But as soon as I draw this arc and I call this one theta, this side will be called opposite. This side will be called adjacent. And what would this one be called?
Hypotenuse.
Hypotenuse. So I have opposite, adjacent, hypotenuse. Now, out of this is our popular expression, SOHCAHTOA. So this is part of elementary trigonometry, which we need to know if you are looking at surveying and in a deeper sense. So this is a sine function. So when I say sine theta, because where we drew the theta, my sine of theta here will be equal to my opposite value here over the hypotenuse. When you go for CA, which is cos, so we have SOHCAH and TOA. The SO is for sine, the CA is for cos, and then the TOA is for tangent. So for the cos 2, the A here is the adjacent divided by hypotenuse. So sine is saying opposite over hypotenuse. Cos is saying adjacent over hypotenuse. But when we go to TOA, which is TOA, it is rather the opposite over adjacent. So the tan theta, tan of this theta, will be the opposite, the value here divided by the value here. That should be equal to tan theta. So there is one aspect of the basic trigonometry, and we need to have an idea about that. How we deal with angles, sine of angles, cos of angles. When you have a right angle triangle, how do you pick the details to fit the formula? Then comes our other friend, Pythagoras theorem, which is saying that if I have another right angle triangle here, and sorry, this thing should be straight, it's bad. Okay. So this is where the right angle is. Let me call this one R. Let me call this one, because of our normal drawing of axis for lines. When you have a graph, this x-axis. Do you agree? And this y-axis. Basic coordinate geometry. Do you recall when you take a graph sheet? All right. So whenever you take a graph sheet and you draw lines, an axis horizontal, you call it x. Then the one vertical, you call it y. So this way y will be here, and this same x will be here. Now, Pythagoras theory tells us that r squared, usually difficult writing on this online. You have r squared to be equal to x squared plus y squared. And this is a very common formula we use a lot when we want to find distance between 2 points. Then the x values will be used to determine the distance along the x by subtracting one from the other. Then the y values should be used to determine the distance along the y by subtracting one from the other. They will yield unique values, and you square each of them, add together, should be equal to r squared. So this that I've written here is what we call the Pythagoras theorem. The same Pythagoras theorem gives surveying a rule. For instance, if you have a right angle triangle and this side is 3, the x length here is 3, and the y length here is 4, this side will be automatically 5. If 3 is also here and 4 is here, you get 5. It's coming still from this formula. Why? 3 squared is 9. 4 squared is 16. So if I put 3 here, 3 squared, 9. When I put 4 here, 4 squared, 16. 9 plus 16 will give me 25. Square root of 25 is 5. So in surveying, when you are dealing with chain surveying, for instance, where you cannot measure angles, you cannot do angular measurement. That is one of the fundamental principles of chain surveying. There is no angular measurement. So in the surveying, and for that matter, chain surveying, where you cannot do angular measurement, the simple geometric figure we tend to use is the right angle triangle. And the rule that we tend to apply is called the 3, 4, 5. And it's coming from here. 3, 4, 5. It can also be 3, 4, 5. So the letters, the numbers can interchange, but the 5 will always be on the hypotenuse. So all that we are stressing here is that when you are doing surveying, you need to have some fundamental computation capability for simple arithmetic computation, for simple trigonometric analysis, and then for simple theorems or laws or rules that we have, such as the Pythagoras theorem. Another one is like, for instance, the area of a circle. We all know that the area of a circle is pi r squared, isn't it? The area of a rectangle, length times breadth. What about the area of a triangle? Have you thought of that? Think about it. So we need to have some basic survey mathematics. We need to understand some simple computation rules and application. The last one, what is the total sum of angles in a triangle? Anybody can answer. What is the total sum of angles inside a triangle?
180.
180. What about a four-sided figure?
360.
If you have a 360, okay, good. So a four-sided figure is 360. is 360. And you are right about that.
Thank you.
So these are some of the simple survey issues that we need to have as we are going along. Even if we have forgotten, we need to pick them up as we go along because they are essential for our understanding. So we need to be able to appreciate that or them as well. So that is with the simple survey mathematics. Speaking of, are there any questions before I move to the next issue? All right, so if we don't have any issue, then we can move on. The next, we want to look briefly at the history of surveying. I'm sorry, the history of map making. And in this, I'll touch on them briefly and fast, but I'll get you the highlights, like I said in the slide, and then you can do some small readings around them as well. Just a brief thing, just to know how map making and the making of maps began, and how we have represented knowledge that we have in the form of a map. And we'll finish off with how maps have evolved over time. So that is what we are going to look at next in our presentation. If there are any questions, like I said, let me know before I proceed. All right, Sheila.
Thank you, sir. Sir, please, the calculation we did, will it come in the exams?
It can come. Why?
I'm
It can
dead.
come. So if you know your mass phobia, start early. But Pythagoras there is a simple calculation around us. If only we did the elementary mathematics or something, we'll touch on it. So if not, then use the opportunity to learn about it. It can come.
Thank you, sir.
And I've shown you how the rule of such things evolve. So in survey, we always say the 3, 4, 5 rule. And any multiple nature of it also works. For instance, from the 3, 4, 5, if I multiply by 2, I can talk of 6, 8, 10. It works. If I multiply by 3, I can talk of 9, 12, and then 15. It works. But the 3, 4, 5 the fundamental, because usually we try to avoid, due to errors, we try to avoid long distance measurement with a chain or tape. So we usually stick to the 3, 4, 5. But it's there. Another one is what I've asked you. What is the sum of the interior angles of a triangle? And a brother said 180. It's a rule. There's even a formula for determining
I'm a
that.
lady, I'm a lady. I'm not a brother.
No, I said the brother told us of it. He answered the question.
It's me.
The 180.
Yes.
Okay, I'm sorry about that.
The name looks masculine, but I'm a lady.
Oh, okay. Thank you for the information.
All
I think
right.
I also switch between panels. There's the one I share with you, and there's the one I work on so that you can see in the shared environment. So at times I leave the platform to work on the other side. Then when I'm engaging you in a calculation or explanation, sometimes I only listen to what you are saying, but I don't know who is really talking. All right, so thanks for the information. All right, so we do it. There's a formula, and I'm sure you may probably. When you have, the formula is n minus 2 into bracket times 180. It will tell you the sum of angles in the polygon. When the n is 3, it's a triangle. It becomes 3 minus 1 minus 2. You get 1. 1 times 180 gives 180 degrees. When it is 4, it becomes 4 minus 2. You get 2. 2 times 180, you get 360. So and so forth. And
So
you
please, the
beat
formula again.
n minus 2 into bracket times 180. This is for finding the sum of the interior angles of a polygon.
Okay, thank you.
There's also another one for exterior, but I won't bother you with that. It is similar to what you've written, but the minus will change to a plus. All right. So there are some basics. Some of them, as you are going along, we'll be dealing with it. Some of them. So that's why I think at least your mathematics should be there. Because when we go to angles and bearings, there's something we call magnetic variation. And there's something we call true bearing. And there's another one called magnetic bearing. It has a mathematical model. When we deal with bearings and angles too, I'll talk about forward bearing and backward bearing. There's a calculation involved. So at least we need some fundamental mathematics to be able to carry along with some of these things. Other than that, we'll run into trouble. So when we get there and you're not comfortable or familiar with it, means you have to quickly sit down and check again after the lecture what was happening there so that you seek help and then cement your understanding as soon as possible. So we move on to looking at the history of map making. The history of map making. And history of map making dates back as far as 2500 BC. 2500 BC. All right. Back then, in those times, it was the Greeks and Arab geographers who were busy involved with the map making concept. And in fact, it is also through them that eventually we will be able to modernize what we are calling cartography, the skills of making maps. So we can trace maps that are as old as in that era, and then those that were quite more current, and then into modern day. So when we go to the era, there are 4 that we are going to talk about. We have what we call the ancient times or antiquity. Then we have what we call the dark ages. Then we have what we call the Renaissance. And then we also have what we call the modern era. So we'll talk about that. It's ahead of us too. So history of map making can be connected to as far back as 2500 BC. And the Greeks and the Arabs were the ones spearheading a lot of the issues then. Then later on, others also joined. But the history hasn't been a smooth one. So different literatures capture different aspects of what they find. So the history of maps has been a bit patchy, not really continuous and solid. So in trying to get to around 2500 BC, we have the figurative maps, where a sort of figure captured is used to explain what they represent on the earth. So we have the Gaza or Nuzzi map of 2300 BC. And this is how it looked like. On the map, they capture mountains, watercourses, and names of places. But they use a kind of figurative representation to talk about it. So this is an ancient trace of a supposed map that was initially having this concept, but as it is made of clay, we've had challenges and breakup of some of the parts. But you can see it is purely symbol representations that are used to communicate what each thing is and what the idea of the representation of the earth back then was. Over period and over time, there were improvements because there was knowledge gain and there was improvement in the science surrounding issues, and a lot of the myths that we used to have were sort of dying down. So the Gatsu or Gasfa or Nazi map is a testament of such that we had back then. Some also call it the era of the clay maps, clay tablet maps. So we have that, and the other descriptions are there. So you have, a location showing Euphrates, and then Babylon. Those were the place names. But that is how they thought things were at the time of representation of these locations or these features. So we have the figurative maps, then by somewhere, oh, what's wrong with my slide? By somewhere 600 BC, we were having the Babylonian maps. And they all that we are trying to say is how people appreciated what were around them and how best they could draw it. So if you compare with modern day maps, at times you see that they were totally not tied to the ground, but they needed to have an idea. So those who were daring and wanted to explore were able to give something. And they had such as representation of issues around them. So how then were we conveying the knowledge in maps? When you want to describe information in a map to someone, how was it done over time? This was done through four main possible stages. We had the literacy, where you use written language to communicate the information in a map. So in terms of communication, you can use literacy, where you write written language, like the map of Ghana is written. So the map of Ghana, the person reads and then understand what you're talking about. Or a street name, or a country name, all those things that you read out. Forest, water body, Lake Busuntre, all those things where you use words. So it's a kind of language, but it's written. So if, for instance, as you have in Ghana, the tree and the fancy and then those things, if you can write it and people can read because they understand the language, because it's fair enough for indicating the information in the map. The second one is what we call articulacy. You speak, and the spoken concept is used to convey the information. The third is numeracy, where we use symbols for representing numbers. In some cases, also numbers. In fact, numbers that we write are even symbols. So here, symbology for map for numbers is the key. Symbology for numbers is the key. Then the last in representing knowledge in maps is called good. So the last one is called graphicacy. Graphicacy, using graphics to communicate. Using graphics to communicate. So these were 4 ways by which we communicated information in a map. We either use the written language concept or we go for the spoken language, meaning that you speak to your friend or to the one who is interested in the map. So these are the 4 ways of representing information in map, or information or knowledge in maps. We can choose between any of these 4. And when you study the issue of maps, that is what they have used over time. Currently, we still do, though spoken may be done like in map reading, where I have a map, you have one in front of you, and I'm talking to you. Identify the contour line with the highest height value, or determine the spot height with the highest value in the map. So I'm speaking to you, and I'm talking about the information in the map. But then you get to some aspects to, then it's about written language. So there are no hard and fast rules. At times we combine 2 or 3 or all in one map discussion. But these are the ways by which convey information in a map. So it takes us to the evolution of maps. What are the evolution processes of maps? And there are 4. We have the ancient times, or what we call the antiquity. And this era captured the contribution and ideology of Herodotus, Aristotle, Eratosthenes, and then the last one is Ptolemy. Please check your mic. Oh. Good. So the ancient times saw the contribution of this geographers. And what were their contribution? You need to look out for that. You need to look out for that. In one of these days, and especially towards your quiz 1, issues on this history issues will pop up a lot. So take note. So we have the antiquity or ancient times. Then we have the second group, which we call the Middle Ages. The Middle Age is also called the Dark Ages. The Middle Age is also called the Dark Ages. It's also known as the ages of the church, because it was believed that at that time, things were done dominantly by the church in their own understanding of what was around them. So with the Middle Age, this was a period when the church, like I said, dominated. And there was an interesting map display. We call the GEO map were developed. And these maps had a very interesting representation of the world. So check and look at what the Middle Age was all about. And then the concept of the GEO maps. What was it about? So that is with the other aspects of the evolution of maps. Like I said, this aspect that we are discussing, some capture it under cartography. Some capture it under cartography. So maybe if it's a typical survey book, you may not find it there. But because it's a mix and we are talking about maps here, I put it over here. But for most, you may find it in map reading, you may also find it in cartography. So we're speaking of the antiquity or ancient times. We're speaking of the Middle Age, or what we call the Dark Ages, where scientific knowledge are given way to the church with their understanding of the world leading. And they came out with so many conceptualization of things around us. Okay, Victoria, you have your hand up.
Yes, please. Sir, thank you for the opportunity. Please, if it was the age of the church, then why is it also called dark ages?
Because knowledge was scanty. Knowledge was scanty, and it was only what people sort of thought and imagined to be around them. So we're not having the advantage of scientific and real representations. Don't forget that this was after the ancient times when the Greeks and Arabs had begun something. So they were not perfect. Somewhere in the course of the Middle Ages, they kind of went to sleep because they were seen to be more scientific, but they went to sleep. So we're not having scientists and other things exploring, but it was the church trying to know things around themselves that were parading and pushing the agenda of the maps and creating their whole for understanding the environment. So that's why typically we call it the Dark Ages or the ages of the church, because we're not having scientific, realistic representation of people's concepts, which most of them were not proper representation. Have I answered your question?
Yes, please. Sir, please, thank you.
Good. So that is what happened for majority of the issues that we have. So after the Dark Ages, we went to the moment of Renaissance, or what we call the Age of Discovery, where there now the quest by people and scientists all over, the drive to get the issues well represented arose. So we call it the age of discovery or renaissance. And it refers to the period of exploration and innovation. So now people were much daring, those who had knowledge and wanted to really convince themselves, push the limits far to get to know what was really happening. And it gave birth to the use of longitudes and latitudes, for instance, in map making. The impact of a more accurate map began to emerge. And they were using a lot of mechanical instruments that was aiding calculation, drawings. And so at that point, some improvements have begun showing forth. Maps were getting more and more accurate. Science had advanced. Technology was pushing the borders. So now we're getting a much better representation of the issues around us. And that was the age of discovery. So many things were discovered that helped us to discard what we felt and had known from the ancient times through the dark ages or middle ages. So a lot of improvement has taken over. People were using more scientific approaches. And such was the experience. Then it moved to the last of the era, which is called the modern era, which has since also improved to this current day approach. And here, the beauty is that complete and accurate view of the world was achieved. So we have had machines, sophisticated instruments. It has also led to the development of the world coordinate systems, which was not the case back then. So every stage took off from the previous. But the disadvantage is that when the church was left to do its own thing and nobody was really interested in maps, then we had the dark age. So all the issues that we are now speaking of became a part of the discussion. Now we are talking about drones, we are speaking about GPS, talking about total station, and all of that. All were happening in the 20th century, and then that was the modern era. Okay, I thought I saw somebody's hand up. So that is with the last and then the fourth one. So we have the first one as antiquity or ancient times. We have the second one as the middle or ages of the church, or what we call the dark ages. Then we have the third one as the age of discovery, stroke renaissance. And then our current, traced back to about 10, 15 years ago, is representing the modern era, where we have instruments that can do more powerful measurements, improving upon accuracy. It takes us to types of maps. Types of maps. And the first highlight is talking about the definition of maps. So we've looked at the issue of map making, but what then is a map? And we say a map is any concrete or abstract representation of features that occur on or near the surface of the earth or celestial bodies. This is according to Campbell, 2001. Some also say maps are is a representation of part or whole of the earth according to an appropriate scale. So that is with the definition of maps. In general, there are two forms of maps. We have the reference maps, and then we have the thematic maps. This is categorization of the map based upon purpose or content. Purpose or content. Then you have the reference maps versus the thematic maps. But I can do categorization of maps based upon scale as well. So I can talk of a large scale map, and I can also talk of a small scale map. Then even where you have a lot of maps, you can even have a medium scale map. But generally, in terms of content and purpose, you are looking at reference maps, general reference maps, or thematic maps. What's the difference? When you say a map is a general reference map, it means a lot of natural and man-made features are captured. So an example of a general reference map, for instance, is a topographic map. A topographic map. Thematic map, on the other hand, is typical sort of maps, specific sort of maps. So they tend to focus on one theme. If it's road network, maybe they may include a little of drainage, but it's dominantly road network. If it's about vegetation, it's dominantly vegetation. They may probably include a few road network because of access to the vegetations or farmlands or whatever. But when it is about vegetation, it's a thematic map. So that is it with the types of maps. So anytime you see a comparison being made between thematic map and general reference maps, then we are looking at content to purpose. But when it's about scale, you can have small scale, medium scale, large scale. Then you can even stretch it further to symbology. So when you go to symbology, for instance, you can talk of grouplet map, you can talk of algorithmic maps, you can talk of flow maps. Then we can also talk in terms of the same maps in the case of qualitative and quantitative maps. So it's all perspective, like it happened with the surveying. For instance, when you have maps which are showing locations of places, necessarily because it's important, but not in comparison with dimension or the magnitude of a phenomenon, like population. So I'll give you the types of maps. I already mentioned the slide, the reference map versus thematic, because those are the two main areas when it comes to survey, although the other forms of that. Maybe we may meet those other forms when we are dealing with the cartography, because here I'm more of survey. Here too, what are the map essentials? This is also a subject that may appear under cartography because the cartographer is the one who makes the map and must have all these essential important things from which to choose and add onto a map. Any good map we sought to use or we produce or we present should have at least a title, should have a date, there should be enough arrow to orient us, it should have a key, a legend, a grid line. At least these things should be fundamental, what have been captured here. There are others that may be captured, they are not necessarily important for the basic things on a map. So every good map should capture at least the title, when it was made, the date, the north arrow, so that it serves the purpose for which we would like to display the things around us. So the next thing that I want you to quickly look at in your own spare distance is the importance of maps and the limitations of maps.
Sir, please, importance of maps and what? I didn't hear the last part, please.
Importance of maps. Importance of maps or map. I think when you make it maps, it leverages it. So make it importance of maps. Somebody's
And you
map
said
is giving us.
limitations of maps.
So we have importance of maps and then limitations of maps.
Larisha, can you mute your microphone?
So look at that. Limitations of maps, importance of maps. Add S to the map to make it maps. The next thing that we will talk briefly about is map skills. This is also vital for surveying and maps that we handle. All maps must have a map skill. These map skills may be represented in one of these three ways. A map skill may be captured as word or statement skill. This subject that I'm discussing here, map skills, you'll find it in surveying generally. You'll find it in cartography because you are making maps, so you need to know what map skills are. You'll find it in map reading and interpretation because we need the map skill understanding to be able to undertake enlargement or reduction of maps. So note it. How do you represent map skills on a map? You can use a statement or a word written form, and that's what we are calling the word or statement skill. Like, let 1 centimeter on the map represent 100 kilometers on the ground. In fact, when you talk of a map skill, it has a rule. A map skill is simply the relationship between dimensions of linear features on ground and their actual representation on a map. So for instance, I have a line such as in a school field. It's rectangular, but I'm talking about only one side. So In reality, the football field may look like this. May look like this. Then I measure here on the ground is, let's say, 200 meters. The map I made, this 200 meters here on the map is rather 2 centimeters. So based upon this information, what is my map scale? So it's a relationship between distance of linear features on the map and their corresponding distance on the ground. So if on the ground it is 200 meters, but on the map it is 2 centimeters, then this is the formula for my map scale. Map scale is equal to map distance divided by ground distance. Map distance divided by ground distance. So in that case, it becomes 2 centimeters on the map is 200 meters on the ground. So the formula will say you have to write as 2 cm over 200 m. So the map scale will be 2 cm divided by 200 meters. So when I say let 2 centimeters on the map represent 200 meters on the ground, I've given you the map scale, but I use a statement to do that. And that is the first form of representation, word or statement scale. The second one is called representative fraction or RF or ratio scale, where the relationship between measurement on the map and actual measurement on the ground is captured as a ratio. So usual practice is that we will write, for example, an example of such map as 1:100 or 1:50,000. So this 1:2 with a colon is the same as ratio-wise 1/100. Because I told you the map scale is map distance over ground distance. In the map, it's 1 centimeter. On the ground, it's 100 centimeters. When you are dealing with the second group, which is the ratio, the unit must be the same. So when I state it as 1 in 100, it means 1 unit on the map is equivalent to 100 of the same units on the ground. So if the unit I'm using is centimeter, it means 1 cm is equivalent to 100 cm on the ground. If the unit I chose is kilometers, it becomes 1 kilometer is equivalent to 300 kilometers. So note the difference. The first one, you use a statement like you are writing English, this and then you use to communicate. But always remember, map scale, you need something for the map and connect it to something for the ground. In the case of the representative fraction, it's the same idea, something on the map divided by something on the ground, or the same thing on the ground, sorry. Something on the map divided by its same length on the ground. But the rule is that the units must be the same. So that is the representative fraction, or what we call the ratio scale. Then the last one is called the graphic scale. the graphic skill. With a graphic skill, usually you have it in the line form like this. Then there's a split with a 0 mark here. And then there are some calibrations with values representing other meters or kilometers. Then there's also another further breakdown to the left of this 0. Those to the right are called primary divisions. Those to the left are called secondary divisions. But the idea is that you have something like a line, which has been split into intervals, and you have a description accordingly. So these are examples to support the math skill. Verbal is the same as the word, is the same as the statement. So you have verbal skill or word skill or statement. Then you have graphic. On this slide, you are seeing the graphic as second. The graphic is what we call the linear skill. The linear skill. And then the last one is the fractional skill, where you express distance as a ratio. Are there any questions? Before I move to the next.
Hello, sir.
Yes.
Yes, I wanted to ask the evolutional processes of of the map making.
Yeah.
The four areas that we have looked at.
Yeah.
Is there any dates? For instance, the ancient times, the Middle Age, the Age of Discovery, and the modern. Do we have any dates in connection?
There are rough dates to it. It's part of the work I don't need to do. There are some rough dates to it. It's not it's more general. For instance, the age of discovery was somewhere around the 15th to 16th centuries.
Okay.
And then the modern era, for instance, was more in the 19th into the 20th century.
19th century.
Most books use 20th century to
Okay.
try and capture the last 100 to 200 years, something like that.
Oh, okay. Thank you
So
very much.
but I'm not that particular about it because I'm just treating it in passing. I just want us to see what happened there, but not really as a historian.
Thank you, sir.
All right. So if there are no other questions, we now want to take some of the survey instruments that we've mentioned and briefly look at them. I'll just mention them in passing in terms of the instrument, but you have to read a brief and make a small note about the functions of each of them. Generally, your work should not go more than a third of a page for every instrument that we are talking about. Shouldn't go more than a third of a page. So it's just a brief thing about what the instrument is and what the instrument does.
Hello. Is that there?
Yes, I am.
Oh, okay.
All right, so we want to look at some instruments that we use or employ in survey activities. And we are going to talk about the chain, the tape, and the GPS total station. The chain and tape may be belonging to the old to medium age instruments. The chain typically being a traditional surveying instrument. The tape, it may not necessarily be a traditional one, but because of the advancements in the use of laser, it is being used, but not as extensive as these more powerful forms for measuring distance. So we'll still talk about it briefly. So that's it. So I want us to look at the chain first. Then we will look at the others. So here I'll run as quickly as possible. When you get the slides, you can read through that. It's self-explanatory. And so if there are any unclear issues, let us know. But it's self-explanatory. And you can at any time check with YouTube videos, online platforms and literature, and you should be okay. But it's important that you have some general knowledge about each of them, because they can have questions there, not only for quizzes, but you can also have questions there for end of semester. So note that. As we discussed, towards those moments and time, I'll share some of the past questions with you. You see, there are times you may be asked to look at a particular instrument, maybe the chain, maybe the tape, and the types of tapes. You may be asked to describe the total station instrument and what are the functions of it. You may be told to do the same for, let's say, total GPS instrument. So we'll just talk about them briefly because we are not doing typical survey, but we need to know them because we use them in survey. And all of these things, if you want videos on them, real videos, you go to YouTube. There are quite a lot so that you can appreciate how they look like. Some even come with the descriptions as you may be having here. So quickly, I'm having the chain. And in respect to the chain, there are types of chain that we have. I've mentioned in the earlier presentation that we have the Ganter's chain, and then we have the engineer's chain. The rest, I let you to choose. Smartly enough, some of the details are here. So, for instance, you are seeing the chain is a steel wire with links connected by steel rings. So
Yeah, we can see you.
Come again.
I said, are you displaying it? It can't. It's not showing.
It's not showing. Are you sure?
Yes, we.
It's showing.
Well,
It's showing. If it's not showing, it's your network. Go out of the platform and connect again.
And then you check. Slide up. Go up.
So just go off
okay.
and then relaunch it again. It will come.
Please, it's not a picture, it's words.
And that says it's not showing. So when it says show, everybody understand that the slide is not being shared or something like that. As for the picture and this, I told you, you have to go to YouTube. In fact, I shared some in the earlier slide, and you may see some here. But the point is that I'm rushing through it. So take your time, read it, take your time, go to the next, take your time, do everything you can to get the details there. So that is the idea. But when it says it was not showing, we felt maybe you are not seeing the slide. So that is the narrative with respect to the chain and then the types. We have all of that there. So the lengths are there. Then this is what I showed in the earlier one. The links in the middle, they're still connectors, the metallic tags that are made of brass. And they're all in the material stroke, your research you will do. So clearly you see the Gantt's chain, you see the engineer's chain. The engineer's chain is, for instance, longer than the Gantt's chain. By how much, you have to think through that and see. By knowing the individual, you will know how much one is longer or lesser than the other. Then these are accessories that go with the chain. They are accessories, support tools that go with the chain. We have the ranging rod. Then we have the arrows. The arrows are what helps us to pin the chain. I told you the chain is heavy. To pin it to a ground and a location so that it doesn't shift. So you plug it onto the ground and then you hold this side. Usually you hold this end here and then press it onto the ground firmly. This side is pointing so that it can go through the soil. Then we can also have pegs. You can also have pegs here. So the accessory, they support measurement on the floor with the chain. So they have their write-ups, you can read about them. Then you come to the compass. The compass. There are two kinds. You have magnetic compass, and then you have the surveyor's compass. Magnetic compass, surveyor's compass. The surveyor's compass is much bigger, more robust, and has fittings below for fixing it on the tripod, the three-legged stand I spoke of when I was talking about level survey. But the prismatic compass is usually small and it's supposed to be held in the hand. So it's not accurate in terms of measurement compared to the survey one, which you can put on a tripod, because your hand has to create that level surface for the prismatic compass. And if you're unable to do it or failure to do it, will affect your reading. So usually when you're using a prismatic compass, there's a level of difficulty in obtaining accuracy as compared to the surveyor's compass. Nevertheless, the compass is also now obsolete to use for accurate survey now, because other instruments like the total stations have come which do a much better work and of high accuracy compared to the compass. So, but we still use it. If you go to an area, you want general navigation and orientation purpose, yes, we still use it. We still do use it though. So we have the pictures of each of them, and the descriptions are there. Then we go to the tape. The tape too is an instrument for distance measurement. There are about 5 models of it. We have the linen, or the one that looks like a cloth. Linen or cloth model. We have the metal, we have the steel, we have the inverse tape. For each of them, the narratives are there. There are some details therein about their weight and other things, and you need to be watching them closely. The inverse tape has an interesting composition made up of nickel and steel, and the ratio and percentage of proportion is there. So that's what you need to watch. All right. So you have the 35 nickel, 65 steel. Some also put it at 34 and 36 nickel, and then 64 steel. So it depends on where you are reading it from, but at least those are the range. 35, 36 versus 65, 64. So that is with the inverse tape. So it's more robust. It can withstand temperature, heat. Because it's a combination of nickel and steel. Can withstand temperature, heat compared to other forms of the tape, like the metallic tape. And like I said, all of this, if only we have time, and I believe you can get and spend some small thing on data, you can always check on YouTube and you see the videos there. Videos are there for us, the pictures are there, everything is clear. At YouTube. So we are not at a lost place at all. So let's do that to enhance the feeling with respect to the instrument that we have mentioned so far. So these are the tape. One form of it looks like. There is the one that is halfway exposed, and then there's the one on the right here, and then there's the type that is concealed in the case, and you only get to see the tape coming out. Then it has a control here for rolling it in and rolling it out. Then you have EDM. EDM stands for Electronic Distance Measuring Instrument. It's a combination of a tube light and a distance measuring device. That one too has its modality, how it works. It sends energy, an electromagnetic energy or beam, from the master to the master is called a transmitter at the master station to a reflector at the other end, and the energy bounces off the reflector and returns. So typically this is how it is. This one is what we are calling the master station. So it is released from this unit and it travels like a wave, hits a target and then comes back. and there is a sign. You will not see the signs. But when the signal gets back to the master, there are circuits, IC circuits, or let's say internal chip that processes and gives you the distance between the station here and the reflector there. And that is how it works. It's an electronic distance measuring instrument. Some also call it electromagnetic distance measuring. They are all correct because the second one is looking at the energy that is used, the laser, an electromagnetic beam. But the first one is looking at it in terms of technology, the electronics. The electronics. Types of the EDM. We have the infrared wave model, we have the light wave model, and then we have the microwave. All of these are the energy. I told you it uses electromagnetic energy. So there are some designed to use infrared. Some are designed to use light. Some are designed to use microwave. All of these, they are energies of the spectrum. When you use your remote in the house, it's using an energy. The energy is provided through the battery you fix in the remote. But when you press and you say volume increase, volume decrease, you are commanding the TV or whatever that the remote is acting on. And when you do the pressing, what happens? The energy is released from your remote control to the TV. But you don't see it because those energy are not visible to our eye. But they are there. So a similar thing has been incorporated in this machine for measuring distance. And these are some of the pictures of the machine. So the energy is released from this unit here. Energy is released from this unit here. Then it goes to the target and comes back. Then we have the total station. That one to the description of it is there. The main functions are there. And then this is how it looks like. Here again, when you go to YouTube, you have a lot of videos, including even how it is set up on the ground and all of that. To give you an idea of what the instrument looks like. As I said, we are just looking at a few of the survey instruments that we usually use around. Then we have the GPS, which stands for Global Positioning System. Global Positioning System. It works with 3 segments. We call space segments, control segments, and user segments. As is suggested, the space contains satellites. The space contains satellites. These satellites are moving around us and transmitting signals towards the Earth. Then there is also the control segment, which communicates with the satellites to see that they are working properly. So in the GPS system, you have the space segment, which has the satellites. Satellite is a man-made, we can have natural satellite like the moon, but the satellite for GPS is man-made, it's an artificial one. So they go around the Earth and they transmit signals, and the signals are received here at the user segment by a GPS receiver. And then some processing happens, and we know our position on the surface of the Earth. That is how the GPS works. So you see the definition, you see the type of segment it works through. And everybody within every segment must work properly. When there's a breakdown with the control segment, for instance, the GPS will cease to function. When there's a problem with the space segment, the GPS will cease to function. When there's a problem with the user, the same thing. So all the 3 segments must work together for us to realize what a GPS does or can do for us. So a brief description of what is contained in the space is mentioned here. The picture here is supposed to aid us understand what is happening. So in the middle here is the Earth. Then in space, we cannot see with our eyes, are the satellites that are moving around the Earth. There are 6 orbital planes there. That's why you're seeing 6 lines going around. And all of them contain a minimum of 4 satellites, GPS satellites, and they are working. So they send signals towards the Earth from where they are. They send signals towards the Earth. And on the Earth, we use GPS receivers under the user segment. I told you there are 3 segments. Space segment, which contains satellites. Control segment, which communicates with the satellite for the system to function effectively. And then user segment, which is devices or GPS receivers that can identify these signals that are coming from space, from the satellite, and use them to determine position. So these are some of the properties of the space segment. The 6 planes, orbital planes are there. Each plane has about 4 to 5 satellites. They broadcast energy, and the type of energy, we call it L1 and L2. And they are nearly taking 12 hours to go around the Earth. It takes 12 hours to go around the Earth. They are launched at an altitude of 20,200 kilometers from above the surface of the ground. That is their altitude, roughly. In space, there are plenty of satellites, but some are for GPS work, some are for remote sensing, and so on and so forth. But they are all there. And they are all identifiable by their various operators. So there's no confusion. So these are control segments. The work that they do is what has been set up here. Daily ephemeris broadcast. Ephemeris is data about location of the satellite in space, which is needed for determining the location of us on the Earth through the GPS receiver. So the GPS receiver that you are holding, as in this picture, this one, the man is holding sample. This one, this is a GPS receiver. And this GPS receiver picks the signals. So the control segment work is to see that these are functioning well, so that information they release to this GPS receiver will be good information. And the kind of information that they have to release include their position in space, although they are moving. We call it the broadcast ephemeris. So that one has to be right for your calculation on the Earth to also be right. Then they check for whether the clocks on board the system. Every system, every satellite has a clock. They have to work well. Other than that, there's trouble. All right, there's trouble. So that is with the space control and user segments. Space control and user segments. Control, these are the functions, what they do. They sell information about satellite location accurately. They check whether the clocks are working properly. If not, then it has to be adjusted or corrected. Then we have the GPS receiver, which belongs to the space segment. Ima, you have your hand up.
Yes, Doc. I want to ask if we can take a short break before we return.
Okay. Is that the agreement of the House?
Yes, sir.
Yes, sir. Some of
All
us are
right.
struggling to follow.
So we break for how long? 5, 10?
Yeah, 20 minutes.
10.
Okay.
Please also, which unit are we dealing with?
Well, for now, because our this thing is organized in 4 weeks, I cannot tie it to the unit concept because the unit is supposed to be 6. So you have to rather follow it through per the subject matter that we are discussing. Do you get it? Ideally, the first four units are supposed to be typical survey activities, and the last 2 units are supposed to be cartography. But with the 4 weeks, it means we need to realign them again. So the best way is to track with what is being done and to follow topic by topic what was treated. Then we can see where we fish out those issues rather than aligning with the unit. Is it clear? The one who asked the question. Is it gone? All right, so I think we are done with the GPS. Yeah. This one talks about how we determine position, and then the position determination is by distance measurement. And the GPS receiver on the Earth, whose position is supposed to be determined, must see 4 of the signals from 4 different satellites. That's the minimum requirement. It must get 4 signals from 4 different satellites in space. And then okay. So that brings us to the end on the survey instrument equipment. I should think so. Let me check the next thing that we'll be looking at when we resume to be sure. Okay. So the next one in the instrument I'll talk about briefly is the level instrument, which I've given you some gist already. Then we'll go to the next major activity where we now look at the chain survey and then some other surveying methods, because now we have an understanding of the instrument a bit. We'll now go to methods and some of the instruments that are used in those methods. So we are going to talk typically about the chain surveying, and we'll talk typically about the traverse. Those are the next 2 major issues. So we'll take a break now. According to my watch here, it's 3:11. I don't know what says, but we are all using the stop clock, and 10 minutes later we'll come back. Thank you.
Thank you too.
Thank you, sir.
Thank you, sir.
Please, what time are we coming back?
10 minutes from now, use your watch.
Okay,
After
thank
10
you.
minutes time.
That'll be
Please, colleagues, which unit are you dealing with?
this
Because since I'm lost.
321.
Hello.
Yes.
Hello, colleagues. I'm asking the unit Prof is dealing with because since
Unit
I
1
cannot
to
follow
Unit
him.
4.
Unit 1 to Unit
He did
4.
not specify the unit. So if you are following him, you will see that he's mixing the units up. Because when he did the history
It
of
will make
maths,
us.
he went somewhere to cartography, but he just said that he can't follow exactly what we have in the book. So let's just
Oh,
follow him with what he is
this
saying.
will be a problem. Because sometimes it seems that the slide he's sharing is different from
Want to do
the books that we
at
have.
least when the slides come, we will be able to show you.
It means that we are not going to get all the information because if you have the book and then the slide he's showing is not in the books, then what are we doing?
He advised that you make your own note as he lectures. So take that one too.
But since the books are being sold out, at least, yeah, I was thinking if I'm able to get a book, at least this
Yes,
thing will follow.
because sometimes the network is not favorable. If he, where I did, it takes the grace of God to give him pass. So if I get the book and then I'm not getting all the information, then it's a problem to me because I can really see that the slide he's sharing is different from the book that we bought.
But he said he
So
was
which
going to
means
give
that
us
we
a
are all
slide
going
at the
to
end
miss
of the
some
lesson.
information.
So there's no pause for an alarm. You just wait when he's done. He will send you the slide. You add the slide to the book you bought, and then you get the additional information. He even asks us to jot things down. So if you want to have additional information, he said we can go online and search for other information because he cannot provide everything for us. And that is what we are supposed to do. He explains what he knows. You go and look for additional information to add up to what he has taught you. So I think it's fair enough.
Madam Spokesperson.
From the orientation given to us, they said when we look for information somewhere we are writing, we should stick to what is giving us. So
So that is what he said, oh. No information outside. Mm.
this is cartography. Oh.
Hold on, Oratuma.
I'm here. Oh. I did.
When you need to give me a call, okay?
Hello?
Hello, sir.
Hello, sir.
Our 10 minutes is up. I'm only seeing 28 people on the platform from nearly 90.
That they will be coming.
Okay. All right. So I'm currently sharing with you the level instrument. Have you seen that?
Yes, dog. Yes, sir.
Good. So when you say you are talking about a level instrument, this is what it is. It's actually a level instrument, but it comes with its own accessory. One of the accessories is a tripod, the leg, the three-legged stand. Then it comes with this long thing we call the leveling staff. The leveling staff. Basically, when you zoom in to the instrument, that is when you take the upper part. Let me go back to this slide and make it big. When I focus on the head, this is what I'm talking about, this side. This is the main instrument. Good. This is what we are calling the leveling tube. This whole thing here. This whole thing here is what we are calling the leveling tube. It contains the telescope with this large end here called the objective lens, and then the smaller piece at the back here, through which you place your eye to watch through. It's called the eyepiece. It is fitted onto a movable base we call the tri-brack that has some 3 screws. You can screw them up. We call them foot screws. So basically, the design of the level instrument is to help us read from the leveling staff a height above every point, like a distance. So the rod provides that distance by placing the rod on every point you want to determine its height. Then through this tube, you read the reading on the staff and note it down in the book. Then later on, after you are done with the field work, you pack everything, go, and then you go and process. And then you get the height of points. Then we can tell who is down and who is up, and so on and so forth. So that is the leveling instrument. So basically, this is how it looks like. So it has the telescope that provides the sight. It has a leveling tube. The leveling tube is the whole of that block there. This whole thing there is what we are calling the leveling tube. The telescope is the arrangement. There are some prisms inside this instrument that direct light through from the outside through this objective lens down and then to your eyepiece. So this whole chemistry here is that the tube, and inside the tube is the telescope, a system of prisms for directing light and for viewing issues. So you have the leveling tube that makes the line of sight. Then you have the leveling head to bring the bubble of the tube at the center of its run. So the leveling head, again, is this one, the tribrac. This one is attached to the tribrac. This one is leveled upon the tripod using the foot screws, these 3 screws. One is here, one is on the other side there, and the one is there. So it's up in leveling the instrument. Then the last one is the tripod. So the telescope, it tells you what's inside the telescope. I told you there are some lenses or prisms therein, and it's supposed to help us see and view things far away very clearly. To help us with a clear view, there's a focusing screw attached to it. So the objective lens I spoke of earlier is a big end, and there is the eyepiece, which is a very small part of the instrument. So there's a tribrac, which is supposed to contain the upper plate and all of that. So this is basically describing how the instrument works. But the idea is you watch through the instrument to read a target value on the leveling stuff, and then you note it down. And then by processing, you use those data to get height of the points. The types: dampy, tilting, automatic, and then digital auto level. Like I told you, the last one, some call it digital level. They don't add the auto, but it incorporates the automatic features in it. We don't want to go into the details because it is not our main subject feature, but we need to know the types. And that should be okay. So these are the pictures of how the damping level looks like. Then from this, we have the tilting. So you see that the level of the sophistication, look at the damping. So robust and simple. Tilting, now you have a lot of joints and screws and hinge. And the idea is it's supposed to tilt. So this part of the instrument, the objective lens, can go up and down slightly because of the adjustments that have been made here. And that's why we call it the tilting level. Then this is the automatic level. Now what you are seeing here is what I was calling the eyepiece. The whole here looks small compared to the one there. The one here is quite big. And that one is the objective. It has a bubble for leveling so that when the thing is horizontal, you can see it is truly horizontal. And then from here, this circular notch contains the the upper plate, and then it's connected to the screws that I spoke of. This one is the digital auto. The digital auto. What makes the digital auto different from the automatic level is that it uses a concept called bar-coded. So what we saw at the beginning, we are calling the leveling stuff. This one, with the numbers written for reading. When you are dealing with the digital auto, it is only this black lines you see, no numbers. Every bar you see here, the black, has a code inside that contains the number. So for the one holding it, you will not see anything to read with this physical text. But when the instrument interacts with the leveling stuff, it picks it. It's like the barcode system on food. When you go to a supermarket and you buy something, you want the price. You get to the counter, they will throw some light on it and you hear picking, and then it picks the price for them on the screen. That's what we call the barcode. It's similar to when you look at books. Behind books, there are something we call the ISBN number, and then some barcodes are also there. So it's a way of keeping data hidden and ensuring consistency and security checks with measurements and other theft and other errors. So with the digital auto, you see numbers. The beauty of it is that it limits a lot of human errors. So it's not about you watching and saying what the value is. The system will pick the bar, decode it, and then have the answer of what it represents. So human errors are limited quite extensively when it comes to the digital auto level. But that is the principle with it. So that's the leveling instrument to add to the other instruments that we have seen. What I want to now go into is the method of surveying. The methods of surveying. And I'll talk about the methods of surveying. Then I will come to the chain and then the traverse as typical survey types that we can conduct. The chain and then traversing. Traversing is a method, but after traversing, where I talk about compass traverse, I also talk about the chain survey. For those who are having the material on the books, so far all that we have been discussing is between unit 1 and 2. So far what we have been doing is between unit 1 and 2. But there are others that are not in that material, and I've told you that from day 1. So if you go depending on only the material, you'll be hot. I've told you their lecture is your key platform. The materials and all those things, they come to enhance. They are not the Bible. So that you think when you have the material, that's it. What I speak is equally important. So when I speak and you don't jot down, you don't take your notes, you can miss certain things. You go to the whatever, even the slides I'll give you, and not everything will be fine in the slides. So those of you are in the habit of staying back and think you have been given slides, you have been given this, I'll go and read. You may miss what I say and what I tell you. So that's why I say make the notes. And where I told you to check with the internet, go and do it. A word to the wise is enough. So that is so far with the instruments and the other issues. So I'm now going to talk about certain methods in surveying and then zero in or narrow down to traversing, and then chain surveying. Then I think I may add even the GPS. I've explained it already in what I gave to you, so I don't need to worry so much head on that. That is, but for the method thing, you need to understand the chain, you need to understand the traverse. It comes with some sketches and plots. So probably in our third lecture, you have to have some massive issues at stake. I want to have time. I don't know. I may start it. If I don't finish it, I'll push it to the last week. So I want to have time. I don't know if evening running the traverse and the work involved will be ideal compared to the Sunday afternoon. So if I'm not convinced we can handle it in the weekday, because I'll not be around next weekend, I'll push it to the 4th week and rather finish whatever I have to quickly so that I can deal with cartography. Then afterwards, maybe come back and see. So those are the issues. Are there any questions before I move to the method?
Hello.
Yes. All right, so I want us to look at methods of survey. This triangulation, I'm going to talk about triangulation a bit and talk about traversing. In fact, it's part of the classification of survey, but this one you are basing it on the method. I think I omitted that when I was dealing with the presentation. I did purpose, I did the nature, and I did the size and shape of the earth. But there is also survey classification based upon the method, and there are two main blocks there. So we have the triangulation, and then but there's triangulation, trilateration, and then traversing. But trilateration, I'll explain briefly. It is used in GPS a lot, but we don't use it in the physical nowadays. But traversing, we still use it for other works. And triangulation is also a bit of an old technique now. A bit of an old technique now. So I'm going to just talk about that briefly. I missed that one out there. So we make an insertion to that. That is classification of survey based on method. So that is that. Then we will leave the main work of chain survey and traversing out for now. Then I'll talk about angles and bearings, and then the concept of errors in measurement. This is very, very key. Then when we are able to go online, I'll continue from there for the, what would I call it? From the errors, then I'll go to the issue of cartography. All right. So so a little insertion. This should have come, I missed out. It should have come when we're talking about the types of survey. So we are looking at classification based upon method. Classification based upon method. So we are looking at triangulation, we are looking at trilateration, we look at traverse. Then from there, we will see to angles and bearings, errors in measurement, survey measurement. Then I'll come back later on to fix the chain. But the kind of analysis I want to do and the explanation. We need time. We need you to have your math sets. And then there'll be construction issues there. Are you with me?
Yes, sir.
Okay.
Yes, Doc. We are with you, please.
All right. So let me do the quick insert for this. But the actual traverse work and the details, I'll suspend it to a later when we have time. We currently have about only 40 minutes. So either way, when I touch it, there'll be trouble, either the chain or the traverse. So I will deal with that in another presentation. At least for each of them, the chain concept, I need a minimum of about 40 minutes to 1 hour for a detailed understanding. Let's say 40 minutes. Traversing, I need around 1 hour because you'll be dealing with some plotting. You have to have that. So I'll urge all of us to get math sets. Get math sets. And not just math sets with a case, but math sets that have complete of issues. your set square, your your set square, your ruler, your pencil, your eraser, your protractor, your compass, your divider. So indirectly, you need to have your own master. Possibly, if you don't have, then you need a new one. You have all the issues there. Are we okay, please?
Yes, yes.
We are okay,
Okay.
sir.
Yeah, we are okay.
All right. So we are looking at classification of survey based on method. And you want to look at triangulation first and foremost. All right, so we are looking at triangulation. Is the first one that I've put up there. This one is not a slide presentation, but more of a material-based presentation that I've launched. So that is the issue. But it's still based on classification of surveying based on method. We have triangulation. Now, when we talk of triangulation, then basically the idea is that if you have a piece of land or an area to survey, you select points or you pick points or you locate points in the area you want to run the survey. And then you link this, any three of the points by lines to form triangles. And that is the idea for triangulation. So the idea is this: suppose I have a land that is of this nature, and I want to survey this one. Then so suppose, as I showed earlier, or as I did work on earlier, there were points. One is here, one is there, one is there, one is there. I'm struggling to use this platform. The idea is to connect this point, form a series of triangles. So from 1, 2, 3, 4, 5 points, I've connected them with lines. I have now 3 triangles connected. That is the idea for triangulation. So you want to determine location of points and picking data, but you are not measuring the data directly. You are rather connecting the data to each other data by a network of triangles. And then You measure the angles between them. These angles will be measured here. There are 3 angles in a triangle. You measure all of the angles one after the other. You keep measuring until you are done. And then when you finish, you pick one baseline in addition to this. So the description of triangulation is you subdivide the area to be surveyed into a network of triangles, as you can see in this write-up. And this classically example of that. So the area is this loop here, but points are fixed at the boundaries of the loop. Then these points are connected by a series of triangles. So when you are at A, one triangle is ABFA. Another triangle is AFDA. Another triangle is BFC. Another one is CFDC. So you can see that the number of triangles that have been drawn, and everything is triangle based. Then the next thing is to measure the angles formed by this triangle. So the whole work entails identifying points, connecting them with lines so that they form triangles. And then your whole area to be surveyed will be seen as triangles connected to another triangle, and in that fashion. So the whole network of triangles are there. Then you measure the angles within this triangle and possibly one baseline. So for instance, in this design, the baseline could be from A all the way to D. It's the longest line that can go through the survey area. This one is not a baseline because it's not going through the whole survey area. This one is not, but this one is. So AD is a baseline. AD is a baseline. But you can see that the whole thing is still a network of triangle, because from here you go to this, you come to that, you come to that. From here you go to this midpoint, you go off, you connect. So the whole thing is a series of network of triangles. The similar thing is the diagram to my right. So in triangulation, you subdivide the area to be surveyed into a series of triangular or network triangles. And then you measure the angles associated with the vertices of the triangle. So that's the next step. The angles in a triangle formed by the 3 control points are measured. So you have to take time. You measure this one. Yeah, the main one is this. So you measure this angle here. This whole angle has to be measured. Then when you are here to this one will have to be measured. This one will have to be measured. This one will have to be measured. And so you have to build it. That's how you deal with triangulation. Because the concept is about forming triangles and measuring the angles there. And the whole work is about the angles of the triangle being measured, and then the network of the triangles. These are the key things when it comes to triangulation. So that is what the write-up is talking about. Then you use trigonometry. I think this question was asked last year. Your seniors, they were asked that same question, and they needed to explain it. All right. Max, is it Max or Max?
Sir.
Yes.
It's like your screen is blank. Okay. Thank you.
Is it okay now?
Yes, please.
Okay. All right, so you first identify points and connect the points with segments or lines, short lines, to form triangles. And another triangle to connect another triangle in that fashion until the whole place is connected as a series of network triangles. The next thing is that you measure the angles of every triangle deemed important in that network. When you are done, you use trigonometry and the measure length of just one side to process the distances of the triangle. The shape of the triangle is important, and that is very critical. For instance, if I should go okay, so if I should reconsider looking at this, the triangles that you form, that you are measuring the angles. What we are saying is that a good triangle should not have an angle that is measured and is less than 30 degrees. Any network of or any triangle you adapt, you connect, and we measure any of the angles. It should be any of the angles. There are 3 angles there. If any of the angles, even if it is 1, is less than 30 degrees, that shape of a triangle is not a good triangle. Not a good triangle. But how do you know? When you connect the lines, you see. For instance, if I take this triangle here, this one will have the smallest triangle angle. This will be the largest. This will follow with that. The longer the lines are to where the angle is being formed, the smaller will be the angle. Okay. So when you measure any angle and it's less than 30 degrees, it will lead you into errors when you use it still for computation. So when it is triangulation, we've said, see your area, subdivide it into a network of connected triangles. Then measure your angle. But ensure that any angle you measure of the triangle is 30 degrees or more. If you encounter one where the angle is less than 30, do your reconstruction. Other than that, when you're forced to use that triangle in the processing, your answer will not be correct. So that is a key part when it comes to triangulation. The area to be surveyed must be split into a network of triangles, meaning that the points that are distributed over the area must be connected triangle by triangle, meaning that you pick 3 at a time of the points to connect. Then when you finish, each triangle must connect to another. Each triangle must connect to another. All right. So that is with the triangulation. The next that we want to look at is traversing. So there is a diagram in connection with just a single triangle. So we have A, B, C. Connected in the straight line form a triangle. And what we are saying that whether you are there with angle BCA or angle ABC or angle CAB, make sure that your measurement is 30 degrees minimum. Other than that, all your measurements should be above 30. Max, your hand is up.
Please, your screen is off again. We can't see the traversing image.
No, then it's your network. You have to go out and come again. Or is that not the case for the others? Are we also not seeing?
It's there.
We can see it's clear. It's clear.
I can see it clearly.
I
My
can
house
see
people,
you.
they've come on.
It's on it.
My house people, my house people. It is not back.
And it's your network. I told you from the beginning, you have to get a good place for your network. And then you struggle with your online work. Yes, Dufie. Or you are not aware you have lifted your hand.
My battery is running down, so I want to if I go off.
Okay.
Yes, most of us.
Abraham?
Sir,
Yes.
please, with a triangulation, after
Mm-hmm.
subdividing the area into angles, you said you have to
You
measure
subdivide the area into triangles, not
into
angles.
subdivide the area into triangles. Okay, thank you, sir. Then after that, you measure the angles.
Yes,
After measuring the
and at least one distance.
okay, and at least one distance.
Mm.
Okay, okay. Then after that, what next? Or that ends it all.
No, you use trigonometric principles. Let me show you one. Yeah, let me use this triangle here. You see, I'm just explaining the method, but I'm not working the method. If I'm working the method, I'm doing pure surveying. But I want to avoid that. But
Okay.
that is the explanation I was giving. Okay, watch this triangle. Have you seen this triangle?
Yes, sir.
All right. Now you see what has been written here, baseline.
Yes, sir.
So what it means is that the triangle is A, B, C, and back to A
Yes.
with these three angles,
Uh-huh.
possibly for measurement, and then at least one distance.
Okay.
Now, when you do that, there is what we call the sine rule, for instance. It's a trigonometric function rule. Sine rule is written this way, sine. There is also cosine rule. So the sine rule, for instance, says this. Let me label the points. This is a baseline. Let's say we call this one 1. And we call this side 2. It's a distance, so it's not just a symbol. And we call this one 3. Now this is the sine rule. The sine rule says that sine this angle.
Mm-hmm.
Oh, let me say it this way. It's the length here, length AB over sine this angle. So let me call this angle, for instance, theta. Let me call this one alpha. And then let me call this one, let's say 5. Are you seeing the signs?
Yes, sir.
Good. So what is the sine rule? The sine rule will be this. I'm using the numbers, but please understand the numbers as distance. So distance from A to B is what I'm calling 1. Or maybe I'll use the letters. So this is how it is going to be. The sine rule says that AB I'm talking about the distance, AB, over, when you take this length, you take the sine of the angle opposite it. So AB over sine theta should be equal to, then I take the next one like this, BC over sine alpha. And this should be also equal to the last one. Which one is the last one? CA over sine this. So this one is called the sine rule. I've always left. 5. So this is a sign rule. Hello. So the practical side of the work is that you, the surveyor, you are measuring only the angles of the triangle. Then at least one length. Master, are you hearing? The one who asked the question.
Yes, I am here.
So you see the emphasis is look at the measurement I did. This is the rule, but in the field, look at the measurement I did. I measured alpha, I measured phi, I measured alpha, this is alpha, sorry. This is theta, and this is phi. So I measured 3 angles and only one baseline. But when I came to the sine rule, I can write the rule and then solve for the one I want in terms of length that I didn't measure in the field. Then eventually I can use that same other science-based processing to determine the coordinates of A, the coordinates of B, the coordinates of C. So I've not shown the details of how we work it out. I'm only describing how the survey is done. So if only you are interested in using triangulation as a method for your mapping, for your survey, then the first rule is that once you see the area you want to map, you will have to place points close to the boundary around the area you want to map. Then by those points and other points within the space, create triangles that connect to each other. When you are done, measure as many as you can of the angles that are forming one triangle as against the other. So you have to visit every triangle and do your measurements. But the rule is that if your triangles were good, you shouldn't have a case where one of the angles you are measuring is less than 30 degrees. If you get such a situation, that triangle is a bad one to work with. So the idea in the triangulation is you subdivide the area into triangles, then you measure all the angles of the triangles. So that's where the work is. You will be seen to be measuring angles, angles, angles.
That's a handy woman. Oh,
Please, Dora, mute your microphone.
Dede, please mute.
So the whole work will be seen as measuring angles, 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 angles. That is the nature of the work. Because you have subdivided the area by introducing points and connecting the points with streets so that you form a network of triangles. That is why the name is saying triangulation. Angular measurement of a triangle. That's the meaning. So you deal with the angles. Deal with the angles mainly to collect the data. Everything will be about angles. Then in addition, you measure only one length distance. A kind of baseline. Then based upon that, you can do computations like this, the sine rule that I've stated here. So with just one side, I can get the other side, I can get the other side, and I can populate it all the way through. But that is typically a surveyor's job. Somebody is doing surveying, you will learn this one in detail. But for us, we are just touching on it in terms of the knowledge. That's why I didn't go into the nitty-gritty of it. But I stated, as you can see in the explanation, that you need to apply trigonometry. And the sine rule is an example of a trigonometric rule. There's another one, cosine. But they all affect the object or the triangle in different ways. So where you have a lot of angular measurement of the triangle with only one distance, the sine rule is the best to apply. But where you have a lot of distance measurement with only few angles, then the cosine rule is the one to apply. So are we okay now?
Yes, but please, sir, our batteries are running, our phones
Hardly
are
hear.
running low.
Hardly hear.
So please, it's past 4 this time.
So we have it that way, that in the triangulation, you connect with triangles, you measure the angles in there, and then at least one distance measurement. Then you can use the rules of trigonometry to work it out. But like I said, we are trying to understand the approach, not to deal with the approach or to work out the approach in detail. The second one is the traverse. And the traverse is slightly different in model to the triangulation. With the traverse, you connect your points that you are interested in by streets or segments, but they must conform to this. You connect them in sequence, this statement. If you are describing a traverse and you don't talk of the connection in sequence, you have not described a traverse. And this is some of the things you have seen in some of you when you are responding to questions. We ask you to describe a traverse, and the person writes, they measure distance and angles, and that is all. Distance and angles in what way? There should be a connection of one survey line to the next in sequence, and that's how you engage the activity. So if you just tell me that you measure the angles, the distances of survey lines and the angles between them, and you don't include connected in sequence, you are not talking about traverse. The whole description is wrong. I'm not talking about traverse. So some of these things, when I'm teaching, I'll be striking them, but I know so people will not pick the details, and they'll come and write what they want to write. Anchor, you have your hand up. Is it anchor or anchor?
Anchor.
Okay.
Sir, please. So in exams, can you explain this in your own words? Because it's not.
Yes,
We
you
cannot.
can explain. You can explain in your own words, but you cannot miss the technicality.
Way.
You can explain it in your own words, but you cannot miss the technicality. And one of them is just what I've highlighted to you. If you talk a whole page and there was nothing that showed that your survey line or your distances were connected one to the other in sequence. This thing is a technical arrangement in sequence. If you don't add it, you've not described a travel. And this is how it looks like pictorially. This is how it looks like. So if you are using this picture, from A to B, from B to C, from C to D, from D to E, that is what we mean by a travel. So if you just tell me you measure angles, distances, and angles, and there is nothing about connection of one distance to the other in a sequence. And when you say sequence, it means one follows the other. And that is how you run the survey. So when you go to the field, like I see in the table, you do AB, you measure it, and you measure the bearing. Then you go to BC. So from A to B, B is connected to C, C is connected to D. You cannot do AB and come and do DE. and come and do FG because you are interested in measuring distance and angle.
Okay, sir. Thank you.
All right. So that is how the traverse is. You are dealing with survey lines that are connected in sequence. And then you are measuring the distances of the survey lines and the angles between successive, another word, the angles between successive survey lines. It's still about the sequence issue. It's still about the sequence issue. But the point is that when I'm measuring, I measure this distance. And I go here and I measure this distance. I should come and measure this angle. From this angle, when I go, I should go and measure this angle. So I'm following the order, arrangement. You don't just measure anyhow because you feel like measuring, but you measure in according to the design, according to the order, and according to how the connections were done. If you don't follow that, you are not describing a traverse. You are just writing words. So that is the traverse. We've seen triangulation, we've seen traverse. This is also another model. So from A, you go to B, you go to C, go to D, go to E, all the way and you come back. So on the field, you measure AB, then you measure BC. Then this angle must be cleared, whether you are measuring the inside one or the outside one, you have to clear it. Then when you go to C, you come and clear this angle. When you go to D, you measure this distance, you come and clear. And you always follow in that sequence. If you don't do that, you are not dealing with traversing. You will struggle with processing your data. We will not deal with processing of the data, but your definition and your explanation and your description must be spot on. All right. So we've seen that of classification of survey based on method. The last one would have been trilateration, but I didn't include that for you. But the surveyors, they do that. So for us, it is the triangulation and then the traversing. Now, depending on, okay, the trilateration is here. Oh, okay. All right. So you said that one in the slide for us. Let me read around it. Depending on the instrument you are using, you see that the traversing definition is not tied to the instrument, but different instruments can undertake traverse. Different instruments can undertake traversing, but traversing stands on its own. So when you talk of chain traversing, for instance, you are using the chain to support you in the distance measurement, not the angle. When you are doing chain traversing, you are using the chain to do the distance measurement. The angles may be done with another instrument. Then you can also do compass traversing, where you are using the chain to measure distance, and then angular measurements are done by means of the compass. Then you can have plane table traversing, and the last one is theodolite traversing. And all of that, the explanations are there, as you can see in this material. Are there any questions? Because our time is up. We didn't start early, but so have to somehow end it. So are there any questions? The next time we meet, we are going to deal with errors in survey measurement, the concept. Then we'll talk about angles and bearings. Angles and bearings. Then we will go into cartography. We'll go into cartography. So that is how we are going to engage the rest of the issues. Abena?
Sir, with the plane table traversing, are they under traversing or other methods?
No, the only reason why it is still measurement, but you use a plane table. A plane table is a kind of survey design setup where you have a table and you have your instruments on the table. So you work everything on the table, including your plotting and everything. So it's a kind of technique, but it's an old method.
Okay.
Yeah, it's an old method. I think it used to be around after the chain, but when we developed advanced instruments, then it was abandoned. So we don't use the plain table. It's a whole design on its own for mapping in the field. Are there any questions, please? All right. So we'll end it here. And like I said, I'll get you the slides and then we'll take it from there. But we have not concluded the rest. I told you, I don't know, Sunday we cannot meet. That I've said already. So after Sunday, between Tuesday and Thursday, we need to pick 2 days, either Tuesday, Thursday, or Wednesday, Thursday, something like that, or Tuesday, Wednesday. You have to pick so that we have 2 hours of engagement, and then we can plan it either 6 to 8, 7 to 9, or 5 to 7 for those 2 days to take care of Sunday's 4 hour that will be missing. But the following week, I'll be coming back. So let us know. The page is there. Discuss the issues and then.
Sir.
Yes.
Thank you, sir.
So discuss the issues and let me know so that we can plan with it.
Okay,
so that I can
Doc.
also inform Moses, the guy that does the recording for us on the moments and periods, so that he can help us with the recording when we are on.
Noted.
All right. So you take good care. Have a nice week, and then.
Thank you, sir.
Hello,
Okay,
Doc.
sir. Thank you.
Hello, Doc.
Yes.
Yeah, Doc, please. This one there, we will play it. We need the slides to add it to our small notes. Since you said the course is a little bit difficult, we will play that if by today, if we not get it today, by Monday, if we get it, so we will be very happy.
Okay.
This course, yeah. Wow.
We are doomed.
Cartography.
This one pass.
Who say man no dey?
Whose land are we going to survey after this?
This
Now
is
you miss
finished
your meeting.
hard.
Feed the children of me. Or we are going
Who
to
say
Meanwhile,
man
ask
no
my
dey?
landlord, come and survey for
my
me.
dad tells you.
They should have.
Are you going to survey the classroom or we are going to survey
Please, after this course, please see me. I'm a surveyor. I'm a
How many
surveyor
try
after
against
this
that
course.
course?
The TA will help us.
Please, can we
You
discuss the date?
you don't know. You meet your meter now.
The date,
Tuesday.
okay.
Let me calculate the number of triangles I can get in my house.
So let's do Tuesday and Wednesday.
I was feeling very sleepy. Now that the class has ended, my eyes clear.
Ayeka.
It's either triangulation or traversing.
My eyes clear immediately.
Okay.
When you want to listen, your eyes will be okay. When it is done, then you're okay.
Boy,
You.
4 by 4.
It will be hard, we know.
God is our helper.
Yeah. How for do? I want means you have to write. You-
Are we going to the top two?
You have no choice. And where are we taking this?
The time is not enough for this course. So if you see what we are supposed to cover and then the time, that is
People
why
that
the
were
thing
saying we should close. Go home till you refuse to go. Be here.
is.
You will come back and start again.
Music. Laba.
Yeah, the whole show cry. Nothing.
Whatever.
This is not
Hey, I was
chat.
hoping when the book. Sure. I was hoping when the books come in, it will be better. And now those who have the book are even
Oh, it's
saying
so
the book has been.
nothing. There is so scanty. The things are very scanty. Point, like that. Very scanty. There's plenty drawings and pictures. So if you don't have your notes, most of the things he's saying is, so it's better we get a big notebook and we write it. I'm telling you.
Oh, with this speed, cry, how do you write? Hmm? Yeah. Okay. Oh.
You say you want to switch. You switch.
I'm going to look for a known surveyor and start looking at.
Well, look for some tape measure and start work. Okay. Start drawing triangles and measuring them. Bye bye.
Let me divide my house into triangles and see how far.
God will take care of everything.
Oh.
These two shall pass.
Yeah, so these two shall pass. Yeah.